Find the Fourier series for f of x equals mod x, where x belongs to range open interval minus pi to pi, and hence reduce the relation 1 plus 1 by 3 square plus 1 by 5 square plus etc. equals pi square by 8. Here we have interval of the format minus a to a, and we have L equals pi. We will check whether function f of x equals mod x is even or odd function. When we draw the graph of modulus x, we have this graph is symmetric about y-axis, which ensures that f of x equals mod x is even function. Let us also check whether f of minus x equals f of x is satisfied here. We have f of minus x is obtained by just replacing x by minus x. Thus we have f of minus x equals modulus of minus x, which is x. Thus f of minus x coincides with f of x. Hence again we have verified that f of x is even function. For every even function we have Fourier coefficient Bn will be 0. We have a0 equals 1 by L integral minus a to a f of x dx, where we have upper and lower limits are pi and minus pi, L equals pi, and f of x equals x in the range 0 to pi. F of x equals minus x in the range minus pi to 0. We have integral minus pi to pi f of x dx, where f of x is even function can be rewritten as 2 times integral 0 to pi f of x dx. In the range 0 to pi we have f of x equals x, and hence we have a0 equals 2 by pi times integral 0 to pi x into dx. By usual integration and application of limits, we will get a0 equals pi. We have an equals 1 by pi integral minus pi to pi f of x cos nx dx. Since f of x is even function and cos nx is also even function, and product of two even function will again be even function, we have integral minus pi to pi f of x cos nx dx can be replaced by 2 times integral 0 to pi x cos nx dx. We have f of x equals x in the range 0 to pi. In order to perform integration, we can make use of integration by parts, treating x as first function and cos nx as second function. First function into integral of second function minus derivative of first function into integral of this function is written here. Since derivative of 1 becomes 0, we will stop the process of integration by parts here. When you apply upper and lower limits, we will get an equals 2 by pi minus 1 the whole raised to n divided by n square minus 1 by n square. We have sine term becoming 0 when we apply both upper and lower limits. Also, only cosine term will give us non-zero terms. We have an equals 2 by pi into 1 by n square multiplied to minus 1 the whole raised to n minus 1. Thus we have Fourier series expansion obtained as f of x equals pi by 2 plus summation n ranges from 1 to infinity 2 by pi n square multiplied to minus 1 the whole raised to n minus 1 into cos nx. When you give different values for n ranging from n equals 1, we will get Fourier series expansion obtained in this format. We have this is a0 by 2, and this is the format summation n ranges from 1 to infinity bn cos nx. Notice that 4 by pi can be taken common from outside each cosine terms. Thus we have f of x equals pi by 2 minus 4 by pi multiplied to cos x plus cos 3x by 3 square plus cos 5x by 5 square plus etc. Since we wish to deduce the result 1 plus 1 by 3 square plus 1 by 5 square plus etc. equals pi square by 8, using this Fourier series representation, let us give x equals 0 on both sides. When you give x equals 0 in the LHS, we have f of 0 equals modulus of 0, which equals 0. When you give x equals 0 in this RHS, it becomes pi by 2 minus 4 by pi multiplied to 1 plus 1 by 3 square plus 1 by 5 square plus etc. X equals 0 is the most appropriate choice because it makes all the cosine terms to 1. And the LHS of the desired result which we wish to prove is clearly visible here. Now, when you take minus 4 by pi multiplied to this square bracket to the RHS, we will get pi by 2 equals 4 by pi times 1 plus 1 by 3 square plus 1 by 5 square plus etc. We have obtained 0 here because f of 0 equals 0. Now, when you multiply both sides of this equation using pi by 4, we will get 1 plus 1 by 3 square plus 1 by 5 square plus etc. equals pi square by 8, and hence the desired result is proved.